both. Right. Again, so send through my usual request, send through topics that you'd like me to go through on. I thought maybe I might just, I got a report back from the first homework from the marker, and there are a couple of points there that he raised that, so maybe I'll talk a little bit about that at the beginning. About the VNs, for example. So we define V0 to be the empty set and Vn plus 1 to be the power set of Vn. Okay, so we think of this as the beginning of the set theoretic hierarchy. Here we start off with the empty set, and V1 will be the power set of the empty set. V2 is the power set of V2, etc. So actually what we have, I mean, from later on in the chapter, what we've got is that actually each of these VNs is transitive. So that's one fact there about the VNs. And most easily seen by induction. The empty set is trivially transitive. Suppose Vk is transitive. Okay, Vk plus 1 is power set of Vk here. So let X be a member of Vk plus 1. Right? So it just means that it's a subset of Vk. To be transitive, we just want every element to be a subset here. So to have Vk plus 1 transitive, we need that X is a subset of Vk plus 1. So I need all of these Zs that are like this to be elements of Vk plus 1. So the report back from the marker was that a lot of people were still getting confused with set elementhood and subsetness or subsethood here. Right? So we need all of these elements to be subsets here. Okay, but X is a subset of V kappa here. Oh, sorry, Vk here. So what I've got here is that Z is a member of X, which is a subset of V kappa. So Z is a member of V kappa. Sorry, kappa. I keep saying kappa, K. So Z is a member of Vk. But by the inductive hypothesis, Vk is transitive. So elements of VK are subsets. But if it's a subset of VK, it's an element of the power set of VK. And this is just what VK plus 1 is. So I've shown that a typical element of an element of VK plus 1 is also in VK plus 1. So any element of VK plus 1 is a subset. So VK plus 1 is transitive. Okay, so it's a kind of watertight little logical argument there. So now we've got that VK plus 1 here is indeed VK union the power set of VK. So it's not true in general that it's not true. Well, let me say that afterwards. So actually here, if we want to prove this, notice that this, of course, just is this. Right? So here, right, all I need is for this equation to be true is for VK to be a subset of VK plus 1. But indeed, that's in effect what we've shown, right? So we've just shown that VK is transitive, right? And so any element of VK is a subset of VK, right? And any of those subsets of VK are elements of VK plus 1. So we have this. So we have this for all Ks. Right?
Why, if it's a subset of VK, it's also in VK plus 1?
Sorry, here, this one?
Yeah, the line before that, just
This one?
the one just above that. Yeah.
Here? This
No,
one?
the one below, just the second last. Yeah.
What are you worried about? This here? Transitive?
Yeah. So why, if it's a subset, if VK is a subset of so if X is in VK and it's a subset of VK, why is it also in VK plus 1?
Because VK plus 1 is the collection of subsets of VK. Because VK plus 1 is the power set of VK. So any subset of VK is an element of the power set of VK. So any subset of VK is a member of VK plus 1. How does that seem? Convinced or not?
Yeah, that makes sense. Yeah.
Okay. So the other thing that reported back was about unions. So some people, I mean, it's always the case at the beginning, as some people get confused about big unions. Right? Suppose I have this set here. So the outer set, it's only got one element, this one. So this element indeed has two elements if A is different from B. Right? That's not important. So I take a big union of this, and it has the effect of stripping off a layer of parentheses. So it kind of just removes the outer envelope of the outermost set. Because after all, what is big union supposed to be? Collection of the set of members of its members. So I'll write it out formally. So it's the set of U, so that there is a V in here, and U is a member of V. Well, in this case, we've only got one thing. V can only be one thing, this set AB. So that U is a member of AB. It's the only thing we have to worry about in this particular union. But now you can see this means U is A or B. So I can think of the big union as just stripping off one layer of outer parentheses here. If I take the big union of this, this is going to say, this big union says, I want the set of members of this set. So again, doing it in longhand here. And so here I've got two possibilities, A or B. And this is asking then for the elements of, well, A or B. So this is the collection of U such that U is in A, together with the collection of U such that U is in B. So of course, this is just A union B in our ordinary little union sense here. Okay, but in general, the slogan is that big U strips off an outer layer. An outer layer of brackets, parentheses here. And so it sounds like, you're looking two levels down. You're looking at members of the set, right? But in fact, what it does, the effect of it is to strip off one outer layer of parentheses there. Okay, are there any questions about that? Yeah, I mean, the other thing to bear in mind is that elements I could take X. I could just, in general, I could take a set X here. And I can take its power set. But that doesn't mean that X is a subset of the power set. So some people were making this error. I mean, if X is transitive, this is true. Because every element of X is a subset of X. So it's over here. So this is true if X is transitive. But it's not true in general. For non-transitive sets, I can't conclude that X is a subset of the power set, its power set. Right? So bear that in mind. There. Okay. I could go through some of the last lot of homework that you just supposedly handed in, or I could do some other topic if anyone has questions. Okay, so let's see. These solutions should now be up on up online on the course website. Actually, so under exercise solutions for chapter 1. So this was one might think perhaps this gives a good definition of ordered triple. Well, so we might want to say, okay, can I define ordered triple, right? Let's say ordered triples like this, using this. Can I make this equals this? And the point of the question is that, you know, if you've got two triplets, x, y, and z, x prime, y prime, z prime, right? You don't want to confuse them by having a bad definition like this. But here the answer is no. If you considered x, y, x, according to this definition here, and x, y, y, they would be indistinguishable because both of them would equal x, y. Both of them would equal this. just by the axiom of extensionality. This, in the case that either z equals y or z equals x, boils down to this. So I wouldn't be able to distinguish between these two ordered triples. So these are indistinguishable. So that's not going to be a good ordered triple. And the second part of the question is just, the exercise is just the same thing. There's another definition there of ordered triple, and that also fails for the same kind of reason. So the way to answer that is to give an example like this to show that it's not going to work. It's not, there are going to be two different things that we want to distinguish, but which the proposed definition does not distinguish. Okay, let me look at 126. I mean, I think there's no harm in practicing our concepts of transitive sets. So 126 says, show that if y is in X, then the transitive closure of y is contained in the transitive closure of X. So recall what transitive closure was. Transitive closure of X is the collection of all of these big U's repeatedly applied to X. So this equaled, well, X, which is we define to be this here, together with big U of X, together with big U of X, together with, and then 3 times like this. So digging down further in the epsilon chains below X. Right? So into TCX, this is just U0 of X is X. Into TC of X, we throw all the members of X. We throw all the members of X. We throw in all the members of members of X, and so on. So this TCX has got no epsilon holes in it. Okay. We want to show TCY is contained in TCX. Well, here's TCX, it's the union of all of these things. TCY, something similar. It will be sufficient to show that every big UN of Y is contained in a big UN of X. It doesn't have to be the same N. Okay, so solution. Pick a Y and X. Then we just show by induction that this holds here. And it's really just about what the definition of the big U is doing here. Well, U0 of y is just y, and that is contained in, well, U1 of x. This is elements of x. Here's an element of x, so all of its elements are in there. So in general, right, we have the same thing. If A is contained in B, then big union of A is contained in big union of B. So I've got U0 of y is contained in U1 of x. Hence, if UN of y is contained in UN plus 1 of x, then UN plus 1 of y is contained in UN plus 2 of x, etc. So this is going to mean that TC of y, which is the union of all these UN y's, are contained in all the union, or the UN plus 1s of x's.
You have to prove that general statement.
I'm sorry? A little
You have
louder,
to prove
please.
the general statement. You have to prove the general statement.
This one here?
No, the one 3 lines above, in general.
No, I don't think so. I mean, I think you can just say that. At least for the purpose of this exercise, yes. Okay, part two is a little bit more interesting in some ways. Gives another way to think of TCX. This is part 2 of that same exercise. It's the union of all the TCYs for Y and X. So actually, this is a basis for, we define TCX in terms of things we hope we already know, the TCYs for Y that are in X. So I throw in, if I know all the TC, if I can compute all the TCYs for a member of a set, this tells me how to compute TC of X. Okay, so here's one method. So we just say by induction on K. We'll show that all of the things in here, some of the components of TCX, right here, are contained in the right-hand side. Let me call this right-hand side Z, so I don't have to write it out again. Okay, so k equals 0, this is trivial, because u0 of x is just x. And clearly that is a subset of z. Okay, so suppose it's true for k. Pick something in uk plus 1 of z, x. Right, so what does it mean for z to be in here? This is the big union of this. So this is saying that z is a member of some member of this here. So for some v in big UK of x, z is in v. Okay, so the inductive hypothesis says that this is contained in z here. So this v here, it's either in here or it's in here. Either v is a member of x, right? So in this case, if v is a member of x, then z is going to be in the transitive closure of v. And we're done. So it's not either or here. Or v is over here somewhere. Or there's some y in x. Okay, or there's some y in x. And with v a member of TCY. So I mean, if v is over here, here, big union, just keeping a cool head, it's a member of one of these members. So v is over here in this big union, it has to be in one of these. So v is in TCY. But then what does that mean? It means that our z here, z is a member of v, is contained in TCY. This is transitive. Any element is a subset. So the z that we picked out, right, a random z that's in here, right, is also going to be an element of one of these TCYs. Right? So z is going to be, sorry, I've used this little z and a big z. Let me go back and amend this. Let's call this W. So that I'm not using not using Z twice. So then Z here is in this W. Okay. Okay, so anything from chapter 2? Can I do anything in number systems here? Okay, maybe I'll just, so question. So there's a question from someone. Can we show that the set of natural numbers only consists of successor chains of the empty set? So recall that the set of natural numbers is the intersection of all inductive sets. Of successor operation chains of the empty set. That's certainly the guiding intuition as to what the set of natural numbers is. Okay, so recall omega, this is the set of natural numbers. Right? So this is the intersection of all of the y's, as the y is inductive. And inductive means being closed under S. So a typical inductive set here, you start out with the empty set and it's closed under the S operation. But there might be other chains in here as well. There might be some other things that are kind of crept in. But being inductive means you certainly have the empty set and you're closed under S operation. So any inductive set is going to have this chain in. And actually, since the intersection of omega, right, is an inductive set, it means that this here must be omega. So we actually have the answer to the question there in the notes. So we show two things, right? Omega is a set. This is proposition 2.3. And then we show that it's inductive. So omega is itself inductive, and this is proposition 241. So it's the smallest inductive set. So, and as clearly this here with just the one chain in it. Thus, omega is going to be this. An n times, etc. So this here is an inductive set. Omega is the smallest inductive set, so omega is this. So the answer to the question is yes. Right. Okay. Another quick question.
In the previous question, you have to prove the other way around as well.
I'm sorry?
in the previous question, do you have to prove it the other way around as well, or is it trivial?
Up here, all this stuff about TC.
Yeah.
Yes. I think, I mean, the other way around is, well, I won't say it's trivial, but I mean, there's something you could say there, but it really follows from part one. If you want to show that this is a subset of this, I mean, we were concentrating on getting this as a subset of this. If you want to go this way around, part one and the definition of TC gives you that X is a subset of this, right? And we showed in part one that if Y is a member of X, then TCY is contained in TCX. So yes, one should say a little bit about the other direction, but essentially the other direction is part one. Okay?
Yep, thank you.
All right. Fine. Okay, good. I'll see you again then later today.